welcome to this problem walkthrough. Today, we'll explore the problem number 987, vertical order traversal of a binary tree. In this session, we'll break down the problem, discuss various approaches, and work through the solution step by step. Let's dive in. In this problem, we are tasked with performing a vertical order traversal of a binary tree. The goal is to group nodes based on their vertical columns, which are determined by the relative position of each node in the tree. Starting with the rooted position, 0, 0, the column value changes as we move to child nodes. Specifically, the left child of a node is assigned to one column to the left, meaning its column is call 1, and the right child is assigned to one column to the right, or call plus 1. At the same time, the row value increases as we move down the tree. Based on these positions, the vertical order traversal requires us to output all non-empty columns in ascending order of their column indices. Within each column, nodes must be sorted by their row values first, and if multiple nodes are in the same row, they should be sorted by their values in ascending order. Finally, the result is returned as a list of lists, where each sublist corresponds to a single column's node values. The input to this problem will be the root of a binary tree. Each node in the tree contains three attributes: val, which is the integer value of the node, and left and right, which are references to the node's left and right children, respectively. The constraints specify that the tree can have up to 1,000 nodes, and the value of each node will be an integer in the range from -1,000 to 1,000. The output of the function is a list of lists, where each sublist contains the node values that belong to a specific column. These values will be sorted according to the rules of row and column order described earlier. Let's look at an example to clarify how the vertical order traversal works. Consider a binary tree where the root node has a value of 3, with left child 9 and right child 20. The right child 20 further has two children, 15 on the left and 7 on the right. The vertical order traversal groups nodes into columns based on their positions. For this tree, the nodes in column -1 are 9. Column 0 contains 3, 15, sorted first by their row values and then by their actual values. Column 1 contains 20, and column 2 contains 7. Thus, the final output is 9, 3, 15, 20, 7. Another example demonstrates a slightly more complex tree. Here, the root node 1 has two children, 2 on the left and 3 on the right. Each of these children also has two children, forming a complete binary tree. For this tree, column -2 contains 4, column -1 contains 2, column 0 contains 1, 5, 6, again sorted by row and then by value, column 1 contains 3, and column 2 contains 7. The resulting vertical order traversal is 4, 2, 1, 5, 6, 3, 7. This example highlights how nodes are grouped and sorted within each column. Finally, let's discuss the constraints and some key edge cases. The number of nodes in the tree is guaranteed to be between 0 and 1,000, and the value of each node is an integer between -1,000 and 1,000. If the tree is empty, meaning the root is null, the output should simply be an empty list. For a tree with a single node, there will only be one column containing the root's value. In the case of a skewed tree, where all nodes are either to the left or to the right, the output will consist of columns in strictly increasing or decreasing order. Additionally, trees with duplicate values must still follow the sorting rules based on their row and column indices first and only use the node values as a tiebreaker. These constraints and edge cases ensure that the solution handles a wide variety of input scenarios correctly. To solve the vertical order traversal problem, we first considered a brute force approach. The main idea here is to assign each node in the binary tree a vertical column and depth based on its position relative to the root. This involves traversing the tree using either breadth-first search or depth-first search. As we traverse, we group nodes by their column indices. Each column holds a list of nodes, and these nodes are sorted first by their row value to maintain vertical alignment. If multiple nodes share the same position, they are further sorted by their values to ensure a consistent order. Once all nodes are processed, we extract the sorted values for the output. While straightforward, this approach has its drawbacks. Although the traversal itself is efficient at O(n), sorting the nodes within columns adds overhead, especially for larger trees. The overall complexity can grow to O(n plus k*log, k, where k represents the number of nodes. This makes the approach less efficient when dealing with deeper or denser trees, as sorting within each column becomes increasingly expensive. As a result, while simple to implement, this method is not ideal for optimizing performance. Instead, we opted for a more efficient approach that leverages a priority queue, or min-heap, to optimize the storage and sorting of nodes. This method eliminates the need for post-traversal sorting within each column. Using a breadth-first search traversal, we process nodes level by level and store their column, row, and value directly in the heap. This ensures that nodes are always processed in the correct vertical and horizontal order. Additionally, a dictionary maps column indices to lists of node values, allowing us to group nodes as we traverse. By extracting elements from the heap, we guarantee that sorting is handled dynamically, reducing the computational overhead. With a complexity of O, n asterisk log, k, where n is the number of nodes and k relates to heap operations, this approach is more scalable than the brute force method. The use of a heap not only streamlines the process but also ensures stability and ordering, particularly when multiple nodes share the same position. This balance of efficiency and simplicity makes the heap-based approach highly effective. There are a few key takeaways and trade-offs to consider. First, the alignment of nodes both horizontally and vertically is achieved by uniquely identifying vertical columns with column indices, while row values maintain the correct vertical ordering within those columns. This insight is central to solving the problem. Second, the brute force approach introduces significant sorting overhead for each column, which can quickly become a bottleneck as the size of the tree increases. In contrast, the heap-based method minimizes this overhead by dynamically maintaining order during traversal. Finally, scalability is a critical factor. The optimized approach is better suited for larger trees since it reduces unnecessary computation and handles edge cases, such as multiple nodes at the same position, more effectively. Ultimately, the heap-based strategy strikes the right balance between simplicity and efficiency, making it the preferred solution for this problem. The goal of this problem is to traverse a binary tree and organize its nodes based on their vertical column index and depth. Essentially, we're grouping nodes that align vertically, and within each vertical group, we sort them first by their depth and then by their value if there's a tie. For instance, nodes at the same depth but in the same vertical column need to be ordered numerically by their values. The final output will be a list of node values grouped by their column indices, arranged in ascending order. To achieve this, we'll use specific data structures. First, we initialize a dictionary to map column indices to lists of nodes. Each entry in this dictionary will store tuples containing the depth, or row, and the value of a node. Additionally, we use a queue for breadth-first search, or BFS, where each entry represents a node along with its row and column indices. These structures will help us systematically process the tree while keeping track of the necessary information for sorting and grouping. With the data structures initialized, we start the BFS traversal. The process begins by adding the root node to the queue, assigning it an initial row of 0 and column of 0. As we process the queue, we dequeue elements one by one. For each node, we store a tuple of its depth and value in the dictionary under its corresponding column index. Then, we enqueue its left child, if it exists, with the row increment by 1 and the column decrement by 1. Similarly, we enqueue the right child with the row increment by 1 and the column increment by 1. This way, we ensure that each node's position in the tree is accurately tracked. Once the traversal is complete, we move on to sorting the dictionary entries. First, we arrange the column indices in ascending order. Then, for each column, we sort the list of tuples by row first to maintain vertical order. If two nodes have the same row, we sort them by their values to maintain deterministic ordering. Finally, we extract only the node values from these sorted lists and compile them into the final result, which is a list of lists representing the vertical order traversal. To implement this algorithm efficiently, the choice of data structures plays a crucial role. We use a dictionary, specifically a default dict, to map column indices to lists of tuples containing the row and value of nodes. This allows constant time insertion and retrieval of node information. The queue, on the other hand, is essential for performing BFS. It ensures that nodes are processed level by level, which naturally aligns with the order in which we assign row and column values. These structures enable us to systematically traverse and organize the tree. A key insight is how we use column and row encoding. The column index groups nodes vertically, while the row index determines their ordering within the same column. This ensures that nodes closer to the root appear first in the output. The sorting logic further refines this by resolving ties using node values, resulting in a consistent and predictable output. Together, these elements form the backbone of the algorithm and provide the structure needed to achieve the desired result. Breadth-first search is a crucial part of this approach because it guarantees that nodes are processed in increasing order of depth. This simplifies the sorting step, as the BFS inherently processes nodes row by row. Additionally, the use of a dictionary with column indices as keys optimizes storage, as it avoids the need for a large and potentially sparse 2D array. When analyzing complexity, the BFS traversal has a time complexity of O(n), where n is the number of nodes in the tree. Sorting the dictionary entries involves sorting the tuples within each column, which has a complexity of O(k*log k) for k tuples per column. Since all nodes are distributed across columns, the worst-case sorting complexity is O(n*log n). Thus, the overall time complexity is O(n*log n). For space complexity, the dictionary requires O(n) space to store all nodes, and the queue requires O(w), where W is the maximum width of the tree. Therefore, the overall space complexity is O(n), making this approach efficient in terms of both time and space usage. Here, we start by importing the necessary libraries. The default dict helps us efficiently group nodes based on their positions, and deque is used for breadth-first traversal of the tree. Inside the solution class, we define the vertical traversal method. The first step is to create a dictionary named nodes to store the values of tree nodes grouped by their column and row coordinates. Next, we initialize a queue using deque, which will hold tuples containing a node and its corresponding column and row indices. The breadth-first search loop begins by dequeuing a node along with its column and row. If the node exists, we add its value to the node's dictionary using the column and row as the key. Then, we enqueue its left child with the column moved one step to the left and the row increment, and the right child with the column moved one step to the right and the row increment. This ensures that we explore all nodes level by level, keeping track of their positions in the grid. Once the traversal is complete, we sort the dictionary keys, which organizes the nodes based on their column and row positions in increasing order. This sorted sequence allows us to correctly group the nodes by their columns in the next step. After sorting the keys, we construct the column_table using a default dict to group nodes by their column indices. For each key, which is a tuple of column and row values, we sort the node values at that position, ensuring the order is consistent when multiple nodes share the same coordinates. These sorted values are then added to the corresponding column in the column_table. Finally, we prepare the result by extracting the values from the column_table in column order. The final output is a list where each sublist represents the nodes in one vertical column of the tree, arranged from leftmost to rightmost. This completes the vertical order traversal of the binary tree, producing a structured and visually intuitive result. Here, we start by importing the necessary packages and defining our solution class. The key method is vertical traversal, which takes the root of the binary tree as input and returns a list of lists representing the vertical order traversal. To organize the nodes, we use a tree map called nodes, where each key is a pair of column and row, and the value is a list of integers representing the node values at that position. This ensures that nodes are automatically sorted by column and, within the same column, by their row. Additionally, we use a queue for a breadth-first search, or BFS, where each entry is a tuple containing the current node, its column, and its row. We start by adding the root node at column 0 and row 0 to the queue. Inside the BFS loop, we process each node, adding its value to the corresponding list in nodes and checking if its left or right children exist. If they do, we calculate their respective columns and rows and add them to the queue. After processing all nodes in the BFS, we shift our focus to grouping the nodes by their column. For this, we create another tree map called column table, where the keys represent column indices and the values are lists of integers. We iterate through each entry in the nodes map, extract the column and corresponding node values, and ensure that nodes in the same position are sorted. This is achieved using collections.sort to maintain the required ordering. Once all nodes are grouped and sorted by column, we convert the values in column table into a list of lists, which forms our final result. This ensures that the output matches the vertical order traversal format, with nodes arranged column by column and, within each column, in ascending order of row and value. To make this implementation work, we define two helper classes. The first is pair, which represents a combination of a column and a row. The pair class includes a constructor to initialize the column and row values, and it overrides the equals and hashcode methods to ensure that pairs can be used as keys in the tree map. The equals method checks if two pairs have the same column and row values, while the hashcode method generates a unique hash based on these values. This ensures that pairs are correctly identified as equal when used in the map, allowing us to group nodes properly by their positions in the binary tree. The second helper class is tuple, which is used to represent the elements in our BFS queue. Each tuple contains a tree node, along with its column and row indices. The constructor initializes these fields when a new tuple is created. Finally, we include the definition of the tree node class, which represents a single node in the binary tree. Each node contains a value, a left child, and a right child. We provide multiple constructors to allow for flexibility in creating tree nodes, whether they are leaf nodes or have children. With these helper classes in place, the implementation is complete, and our solution effectively handles the vertical order traversal of any binary tree. To solve this problem, we start by initializing two key data structures, a dictionary called nodes to store values grouped by their column and row indices, and a queue to facilitate a breadth-first traversal of the tree. The queue is initialized with the root node, which is at column 0 and row 0. We then begin processing the nodes in the queue. Starting with node 1, which is the root, we record its value in the node's dictionary under the key corresponding to its column and row, which is 0, 0. Next, we enqueue its left child, node 2, at column -1 and row 1, and its right child, node 3, at column 1 and row 1. This sets up the structure for us to process the rest of the tree systematically. After processing node 1, we move to node 2. Since it is at column -1 and row 1, we add its value to the node's dictionary under the key -1, 1. We then enqueue its left child, node 4, at column -2 and row 2, as well as its right child, node 5, at column 0 and row 2. Similarly, when processing node 3, which is at column 1 and row 1, we update the dictionary and enqueue its children, nodes 6 and 7, at columns 0 and 2, and 2 and 2, respectively. For the leaf nodes 4, 5, 6, and 7, we simply add their values to the dictionary under their respective keys without enqueuing further children. Once all nodes are processed, the keys in nodes are sorted first by their column and then by their row. Using this sorted order, we group the values by column to produce the final output of 4, 2, 1, 5, 6, 3, 7. In the next example, we consider a left-skewed tree, where each node has only a left child. We begin by initializing the node's dictionary in the queue, just as before. The root node, 1, is at column 0 and row 0, so we add its value to the dictionary under the key 0, 0. Then, we enqueue its left child, node 2, at column -1 and row 1, since it is one level deeper and to the left of the root. This setup allows us to follow the same systematic process of traversal and recording. Continuing with node 2, we add its value to the node's dictionary under the key -1, 1, and then enqueue its left child, node 3, at column -2 and row 2. Finally, when we process node 3, which is located at column -2 and row 2, we add its value to the dictionary under the corresponding key. With no further children to enqueue, we proceed to the sorting and grouping step. The keys in nodes are sorted as -2, 2, -1, 1, 0, 0, and we group the values by column to obtain the output 3, 2, 1. This structure highlights the vertical ordering of a left-skewed tree. Now, let's examine a tree where multiple nodes share the same column and row. Starting with the root, node 1, we initialize the node's dictionary and queue as before. Node 1 is recorded at column 0 and row 0, and its children, nodes 2 and 3, are enqueued at columns -1 and 1, row 1, respectively. For node 2, we add its value to nodes under -1, 1, and enqueue its right child, node 4, at column 0 and row 2. This setup reveals how we handle cases where a node has only one child. For node 3, we update the dictionary with its value at column 1 and row 1, and enqueue its left child, node 5, at column 0 and row 2. Finally, we process nodes 4 and 5, which both occupy column 0 and row 2. Their values are added to nodes under the same key, and we ensure these values are sorted as 4, 5. After sorting the keys as -1, 1, 0, 0, 0, 2, 1, 1, we group the values by column to get the output 2, 1, 4, 5, 3. This example illustrates how nodes sharing the same column and row are handled by sorting their values before grouping. To analyze the time complexity of our solution, we can break it down into several key steps. First, the breadth-first search, or BFS traversal, allows us to visit each node in the binary tree exactly once. For each visit, we handle the node's value by storing it in the node's dictionary and potentially adding its children to the queue. Since there are n total nodes in the tree, this traversal step runs in n time. Next, after the BFS traversal, we need to sort the keys in the node's dictionary. These keys represent unique column, row pairs, and if there are k such keys, sorting them with Python sorted function takes k*log k time. In the worst-case scenario, where every node corresponds to a unique column, row, pair, k would equal n, leading to a sorting complexity of n*log n. The next step involves sorting the node values associated with each column, row, pair. For every pair, we have a list of values representing nodes at the same position, and these lists need to be individually sorted. Since there are n nodes collectively distributed among the lists, the total sorting time for all these values is n*log n. After sorting, we construct the final result by grouping the nodes column by column. This grouping step involves iterating over the sorted keys and aggregating their corresponding values, which takes n time. When combining all of these steps, the overall time complexity of the solution is n*log n, with the dominant term arising from the sorting operations. For space complexity, we start with the auxiliary data structures used. The node's dictionary stores mappings of up to n nodes in the form of column, row, pairs to their respective values, which requires n space. Additionally, the queue used during the BFS traversal holds up to w nodes at any given time, where w is the maximum width of the binary tree. In a complete binary tree, this width could be as large as n/2, so the queue also requires n space. Beyond this, sorting introduces additional overhead. The sorted _keys list, which holds up to k keys, adds k space, and since k can equal n in the worst case, this contributes n. Temporary buffers used during sorting also scale linearly with the number of nodes, contributing another n. Therefore, when combining all these factors, the overall space complexity of the solution is n. To put this in perspective, we can compare the optimized approach to a naive one. The naive approach would involve storing all the nodes in a single list along with their respective column, row values. Sorting the entire list based on these pairs and then grouping the nodes by column would result in a time complexity of n*log n, with additional overhead for the grouping step. The space complexity would remain n, due to the storage of nodes and auxiliary structures. The optimized approach, by contrast, leverages a dictionary to categorize nodes during the BFS traversal. By sorting only the necessary keys and associated values, it avoids redundant operations while maintaining the same time complexity of n*log n and space complexity of n. This makes the optimized approach both efficient and streamlined. Finally, let's break down the best, average, and worst-case scenarios for this algorithm. In the best case, where the binary tree is highly unbalanced, such as a straight line, the BFS traversal takes n time, and the sorting operations are minimal. In the average case, we consider a balanced binary tree. Here, the sorting of column, row, pairs and node values contributes to the n*log n time complexity. The worst case occurs when the tree is complete or has a large number of unique column, row, pairs, causing the sorting steps to dominate with n*log n complexity. Mathematically, the BFS traversal and sorting steps scale with n, and since sorting is the dominant operation, the overall time complexity remains n*log n, with space complexity consistently n. When solving this problem, there are several common mistakes to watch out for, starting with column and row assignments. It's easy to mix these up during traversal, especially in BFS or DFS. Remember that for the left child, you decrement the column index, and for the right child, you increment it. If this adjustment isn't done correctly, the values can become misaligned. Another frequent issue arises with duplicate column conflicts. When multiple nodes share the same column, failing to sort them by depth first, and then value if depths are equal, can lead to incorrect outputs. Sorting efficiently is also critical. Instead of sorting the entire list of nodes at the end, which can be computationally expensive, consider organizing the values by column during traversal. This reduces redundant work and improves performance. Additionally, don't overlook edge cases. For instance, empty trees, single-node trees, or trees with extreme depths can all introduce runtime errors if not handled properly. Lastly, in BFS implementations, be mindful of space usage. Storing unnecessary details in the queue, such as entire nodes instead of just values and indices, can waste memory. Optimizing your queue structure will ensure efficient space usage. Now, when preparing for interviews, there are a few key insights to keep in mind. First, understand when to use BFS versus DFS for tree traversal. BFS is ideal for level order processing, while DFS often works better in recursive approaches. You should also be ready to justify your choice of data structures. For example, explain why you used a queue for BFS or a priority queue for sorting. Clarity and efficiency are essential during interviews. Avoid overly complex code when a simpler solution can achieve the same result. Be explicit about how you handle ties or conflicts, such as when multiple nodes appear in the same column. This demonstrates your ability to think through edge cases and resolve them effectively. Additionally, always analyze the time complexity of your solution. Being able to explain why your approach meets the desired complexity is a skill that interviewers highly value. If you'd like to explore related problems, LeetCode 314 focuses on a similar task of vertical order traversal, while LeetCode 102 and 199 explore level order traversal and the right-side view of a binary tree, respectively. Practicing these can deepen your understanding of tree traversal techniques. For alternative approaches to the problem, you could consider using DFS with sorting. In this method, you perform a depth-first traversal to collect nodes into a list, where each entry is a tuple of column, row, and value. After completing the traversal, you sort this list. While this approach is straightforward to implement, it comes with higher sorting costs, typically O(n) log n. Another option is BFS with column grouping. This involves using a queue to traverse the tree level by level, grouping values by their columns as you go. The advantage here is that you avoid the need for post-processing sorting, making it more efficient for larger trees. However, each approach has its trade-offs. BFS, for instance, may use more memory due to the queue, but it's generally easier to implement for level order scenarios. On the other hand, DFS tends to be more memory efficient for smaller trees but can lead to stack overflow issues with very deep trees. Choosing the right approach depends on the specific constraints and requirements of the problem you're solving. Great job! We've successfully tackled the vertical order traversal of a binary tree problem. Remember to keep practicing and applying these concepts to similar problems. Thank you for joining me, and don't forget to like, share, and subscribe for more problem-solving walkthroughs. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!